Uh, so I want to, so this is a number 2, and then I have essentially derived Clapeyron equation, which is the phase boundary between the temperature versus time, and the line between this has to obey those relationships, right? And then what I can do is, there are interesting example, phase diagram, a phase line boundary between solid and the liquid. So let's do that first, and then once again I'm going to draw. Here I'm going to draw 2. Okay, and so solid is here, and obviously the temperature-wise, higher temperature you're supposed to get a liquid, solid at low temperature. And gas is somewhere down here, but I just want to draw the line of the pressure versus temperature for compound. And this is a case where you have dP dt is positive. Okay. Do you see that? Okay. What about here? I'm going to draw, it's not, I'm just exaggerating. Okay. Sometimes you see that, and this is a case where your phase boundary is dP is negative. People has done that experiment. Okay. This is a case for CO2 and others. Okay? And this is what I call the normal. Okay? This behavior is normal. This is a behavior of, unfortunately, the most abundant chemical that we know, which is the water, which behave in an odd way. And their dependency is negative. And people know that. You can do this experiment. You have a compressed chamber, you apply the pressure, you see whether it's a liquid or solid has been melted or not. You can construct this diagram to get this. And from the simple understanding about the delta G equation, now I have a clue, right? So think about it. Let's just talk about solid to liquid transition along this line. So I'm talking about solid to liquid transition. Okay, solid to liquid transition to be consistent. What is my delta Sm? Is it positive or negative for solid to liquid transition? Which is liquid minus solid, right? Is it positive or negative? Clarice?
Positive?
That's right. How about this? Obviously, this is a philosophical argument, right? It has nothing to do with it. This is a positive. This is positive. So if you look at this, now I'm going to do, it is always positive. There's nothing you can do about this. But what about this? It's a molar volume change. And for a liquid and the volume, delta Vm, which is a volume as a liquid, volume as a solid, right? In normal case, right? If I have a liquid, this is my fingers are liquid, okay? Finger points are liquid. They are kind of moving around, right? These are the liquid. When you're solid, they are like this. They're on a regular lattice. So if you guys jiggle around, that's more like a liquid. Okay, it's a fluid that can flow, but you are kind of firmly sitting on your location, which is probably condensing more, and then the volume is smaller. So this difference is kind of small, but it's always, I'm expecting this to be larger. They occupy more volume, and that. So therefore, normal cases, this is also positive. You see this? When this is a positive, what slope do you expect? Positive, and that's the one. But we all know this is a glass of water. You can put on ice. This is ice, right? What's that telling me? For ice, water, Vm solid, they occupy more volume than Vm liquid. So therefore, in this water case, delta Vm is a negative term. That's something that is funny on this. So therefore, this slope is a negative slope, right? dp dt, which is slope, is a negative here. And so that's something that peculiar about the water that has an opposite kind of a trend. This is a little side note. Temperature versus volume. You know, when you do the increase the temperature, what's going to happen? Things expand, right? That's always the case. And at 0 degrees C, I'm saying that instead of volume is jumping it, you have a small, I mean, it's not a huge decrease, but the volume is actually lower, more condensed in the liquid. So this is a solid, and this is a liquid. That's what I'm saying, that the volume is changing. And then actually they continue to do, and then actually eventually they will go up. There's a lot of things going on here, okay? At 0 degrees C, and you know what is the temperature that has the lowest volume for the water? That is, in the liquid phase, that's about 4 degrees C. Okay. We still do not understand completely. We just know that this has something to do with the hydrogen bonding of the molecule that makes this. The whole thing is responsible. Instead of, most cases, molecules are packed this way, right? Waters, we are talking about packing of this molecule, right? It's a bent molecule. How you're going to do it? And when they are in the liquid phase, actually they form these hexagons. H O H O H. So they form this hexagon molecule, and so actually all of a sudden they expand a little bit. And the hydrogen bonding is the lowest at 4 degrees C. And I don't know, in the biochemistry lab there is something called, have you guys heard about cold room? Yes, we have in the chemistry department a cold room. Have you heard about that? Anyone heard about? It is a room that is cold, and the temperature was controlled to be about 4 degrees C. And that's the one that is really the maximize the hydrogen bonding and the separation. The proteins are stored, and you don't want any denaturing the protein and so on. So that's why the temperature is meant to be this way. And there are another protein storage which is minus 80 degrees. You want to just defreeze it so that you can maintain it. But when you're putting protein mixtures in columns and trying to separate them, you need to bring them in a cold room, and you don't want to risk any kinds of denaturation of your protein that is so valuable. So, and it has something to do with the nature about this. This is hydrogen bonding is still quite a complex interaction. I'm starting to bring in the idea about the interaction of the molecule here. Okay, so this is a solid liquid boundary. The exceptional property of the water has to be mentioned. But now really the holy grail of this one is this. Liquid and the gas line. And I want to know, and particularly this one has a name. This pressure here, you know what we call this pressure in the phase diagram? We call this one as a vapor pressure. Okay? Isn't it? I mean, it should make sense to you. You call that when you have a liquid vaporize, create a pressure in equilibrium with a liquid, right? So therefore, for corresponding to temperature, there is a vapor pressure, right? So one thing that you guys already know, when this is a 1 atm pressure for water, I guess the water you have to have this negative slope. This one is 100 degrees, right? When you are at the top of when you move on to the Denver, right? You are not 1 atmosphere pressure. Your pressure is a little bit less. So water boils at not 100 degrees C, something, I don't know, 98 degrees C, 95 degrees C. So that's why it's, if you want to cook the pasta in the high altitude, which is the ambient pressure is low, and then the boiling temperature or transition temperature is lower. And I want to know, have a predictive quantity that is related, and which one is going to control this? And very naively speaking, delta Sn, right? And then how the delta Sn is related, delta H. And for the transition, and what kind of transition we are talking about? Vaporization, right? So heat of vaporization is the one dictate how stiff, how slow the equations are. And I'm going to drive the equation to show you. And that becomes a Clausius-Clapeyron equation. So we come a long way. And finally, we talked about entropy, Gibbs free energies, Born square, Maxwell relationship, everything. And finally, you got something that you can use for the real application. And this is something about making the liquid into a gas. So that was a phase boundary. So now the number 3. It is a liquid and a vapor phase boundary. And you guys can try this, and this Clausius-Clapeyron equation is not hard to do. What I need to do, is there are 2 assumptions that I'm going to do, but let me do start with a Clausius equation, Clapeyron equation, which is temperature relationship is nothing but delta Vm, delta Sn. That one I know. And then so on. The number 2 is particularly we are interested in this. So delta Sn, I'm going to say vaporization. That's my particular situation. So the vaporization is T vaporization temperature delta H vaporization temperature. Somebody said, well, so boiling temperature delta H. I think vaporization is good. Somebody will either they can write this. Okay. So remember, this is always come from ds is Q reversible over temperature. And I told you that this is a perfect example where reversible equilibrium process temperature is constant and reversible heat is defined by enthalpy changes, so that I can use that. So by combining this, I can come about a new equation. So if I combine these 2, and I'm having equation that is somewhere, which is now T boiling, okay, and then delta vaporization molar volume, and the delta vaporization H. Okay, so far so good. And then I'm going to have a one assumption here. So let's think about this, which is a case number scenario. What do you mean by vaporization molar volume? So that must be a molar volume of a gas minus molar volume of a liquid. All right? Can I neglect? Can I do that? That makes my life easy. So I am going to say, if you have this amount of the water, if you're vaporizing it, it occupies a humongous volume. So what I'm going to say is, I am going to kind of make it this one to be not counted. And then all of a sudden this equation, I'm in business, okay? Because I don't want to deal with delta V. So this is a temperature, boiling temperature. And then this is a molar volume of a gas. So that's a first assumption. This is assumption number one. Assumption number one. What is my other assumption? The gas is? Yeah. Do you want to do the real gas? I don't want that, right? Ideal, like I said, ideal. Actually, I think I probably were able to talk about the ideal solution. Ideal solution theory is not good, okay? Ideal gas law is very good, so it's very useful. Ideal solution works on very limited cases, and that's what I'm going to contrast also today. So what am I, number two assumption is, number two assumption is ideal gas. And all of a sudden that I'm in business. So the molar volume on this is P over RT, nRT, so it's RT, right? So that's what I can put it in. And then all of a sudden that this equation, and I'm going to drop this, the boiling temperature, I just say that that's a temperature for boiling. I'm just using a simplified notation there. And finally, I can derive the equation, what is known as Clapeyron equation. Somebody derived this equation in a few lines and they put their name in the textbook, right? I mean, it's not the only job they did. Okay, so that's this. Once again, there was a before, and now all of a sudden that temperature was there, and then RT over P, right? And the delta H.